Greetings, I'm Blackjack Fitz, and the puzzle that you see on the screen is not the puzzle that I'm going to be doing in today's video. Rather, this is a puzzle that I just launched with The Pedaling Pianist. So we collaborated. Take two. Let's try that again, but this time in English. All right. Greetings, I'm Blackjack Fitz, and the puzzle that you're seeing on screen is not the puzzle that I'm going to be doing for the video today. Rather, this is a puzzle that I just put out with The Pedaling Pianist. We collaborated on this puzzle when we discovered that we were both simultaneously working on a Somedoku octopus puzzle. And this is the puzzle that came out the other end of that process, and it's a puzzle that we're both quite proud of. So I'll have a link to this puzzle in the video description, but the puzzle we're actually going to be doing today is this puzzle. Now, you might think that doesn't actually look very different, and that's because it has very similar both aesthetics, obviously, but also the rules are pretty comparable as well. So as we were creating our collaborative puzzle, we were both thinking the other person should publish it on their page and take the lead on that. And so the Pedaling Pianist and his as an incredible setter just decided, well, I'll just set a second one independently, and that way we can both publish one. So it's a nice effort that we were able to get a puzzle that sort of has my sort of signature thing, the Somedoku rule set, and his signature thing, the octopus puzzle, and do that together and put something out. So we're quite proud of that. But in today's video, I'm going to try to solve his solo project, which is Captain Calamari. So let's go ahead and read the rules here. We've got Somedoku. So fill each cell with a digit from 1 to 9, not necessarily 1 through 7. So you can see that this grid is not a 9 by 9, but it's actually a 7 by 7. So we're going to fill each of these, but the digits can go up to 9. So that's important to note. For every row n and column n, there are exactly n different digits. So here in row 4, we're going to have 4 different digits. So if, for example, this was a 1, 2, 3, and 4, then these digits would have to be from 1, 2, 3, and 4, because we already have our 4 different digits in row 4. And the same exact logic will be true in the column. Octopus. Draw 8 tentacles, all the same length in number of cells, that emanate from the head, that's here in row 4, column 4, and reach the edge of the grid where they stop immediately. Tentacles do not cross or overlap, except at the head. And opposite tentacles are considered as single lines, which have 180-degree rotational symmetry. So what that means is we're going to actually end up drawing lines through, let's try that again, through this sort of central cell. And then this line, if I didn't make them all black, it might be easier to see. So let's take a look at this pink line here. That pink line is going to be considered as one line. It can do something maybe like that. We've got to do, I don't know, that doesn't quite look right, but it actually, what does it do? Let's see. I think it does that like this. Okay, so that's 180-degree rotational symmetry, because you could imagine if you took the entire grid and rotated it 180 degrees, the lines, that pink line would look the same. Okay, now all of these lines are going to be parity lines, i.e. the digits or adjacent digits on the line must include one even and one odd digit. So if we imagine this pink line was a line, and this was a 7 in the final grid, then this cell here would have to be either 2, 4, 6, or 8, because those are the only even digits. And we have to go odd, even, etc., all the way through the grid. Okay, and then obviously we can't have, for example, this line do something like this, because it would be crossing over, and that is too naughty. It breaks the rules that they don't overlap. And this pink line can't sort of do that. There can't be branches coming off. That would be a weird octopus tentacle. All right, what else do we have? Now we've got counting octopus. So a digit on the octopus shows how many times that digit appears on the octopus. So if this was a 7 here, then everywhere in the grid that is covered in octopus, there would have to be 7 sevens on octopus tentacles somewhere in the grid. All right, we've also got counting anti-octopus. So a digit that appears in the puzzle but never on the octopus shows how many times it appears in the puzzle. So let's say this digit was a 2, and nowhere in the grid is there a 2 on the octopus. Well, then there would have to be some other 2 somewhere, here for example, that wasn't on the octopus, because there needs to be 2 2s not on the octopus, right? Okay, so to clarify, a digit n either appears n times on the octopus and any number of times off of it. B, n times off the octopus. That's what we just showed with a 2. Or C, not at all. So there can be digits that don't appear anywhere in the puzzle. And we've got a couple of local constraints. This is normal killer, so digits in a cage. Oh, well, not quite normal killer. Digits in a cage must sum to the indicated total. So they could, in principle, those could be 2 5s. That's okay. These digits will sum to 15. And an inequality sign points to the smaller digit. So this digit, if this was a 2, this would have to be 1, because 1 is the only digit smaller than 2. And that somehow is all of the rules, which is amazing, because for a Somedoku, that is a very sparse looking grid. Now, before we get started, I do want to acknowledge the fact that this is not the first time I've looked at this puzzle. I haven't solved it. I don't know the solution path. I'm not quite sure. I'm hoping that we can get through this, but I actually did look at this on stream yesterday, and we got confused by one of the rules and ended up down like a sidetrack path. And so after a while, we figured out the puzzle broke. And so we reached out to the pedaling pianist, and he clarified the rules and clarified them in the puzzle description. So that's all clear now. But so I have thought about this puzzle a little bit. That being said, when the puzzle broke, we got to the point where we realized we needed to basically start over again with some knowledge about the puzzle, but it was going to be like a restart from scratch. So I'm very unclear as far as like the solve path goes. So that's going to be new, even though I think some of the logic to get started might be somewhat familiar in my brain. That being said, I'm doing this one solo, so I don't have Twitch chat to help me today. So we'll see how that goes. A little nervous for it, but let's go ahead and try to start the puzzle here. So what I want to begin by thinking about is the total number of cells that are going to be on an octopus. So the total grid size is 7 by 7, so that'll be 49 total cells that we have to work with. But there's 4 different lines, meaning only 8 cells in the perimeter can be contacted, because we can't have a line that does that, for example. That's just by the rules. Once it reaches the edge of the grid, that's the end. So we can only get 8 different cells in principle. I don't know what the actual cells are, something like that. We can only get 8 around the perimeter. So then we could get a maximum of these 25 cells plus 8 in the perimeter. And that gets us to 33. So that's our sort of upper bound, is 33. The lower bound would be if we just sort of directly go straight there without any wiggles, right? If we took all of these lines and just went straight to the edge of the grid. And here we would have 1, 2, 3, 4, 5, 6 cells on each line. So that's 24 plus the middle cell is 25. So we're either looking at 25 cells or, well, between 25 and 33, right? Sorry, I'm trying to clear all these up. Okay, so we're 25 to 33. Now, what would happen if we did take a wiggle, right, before we got to the edge of the grid? Now we've got 1, 2, 3, 4, 5, 6, 7, 8 cells on each line. So that's 38, 16, 32, plus the middle is 33. So we're in one of two potential worlds. Either all of these lines head directly to the perimeter, and they don't have to go in a straight line, but they, this line, for example, could do this, or this. That's fine too. So it doesn't have to be, a direct straight line, but it has to always be headed towards the perimeter, meaning it can only take 3 cells from the sort of head before it reaches the perimeter on each tentacle. In which case we have 25 total cells that are going to be in the grid. Or we have a world where we've got 4 cells coming off, and then we're at 33. So it's going to be 25 or 33. So let's just take a look at this here. If we could have 25 in one situation, or we're going to have 33. Now, what I want to do, actually, I want to think about these two different worlds kind of in isolation. So I'm going to get rid of these lines. I want to, so yeah, that's one possibility here. I'm going to take a red line and just do this. So this is the black world. That's black. This is what's happening in red. Oh no, that's the opposite. So this is red because it's taking 25 cells if the lines are... Sorry, what I'm trying to do is represent visually what it would look like. So red is where all the legs go straight to the perimeter of the grid. And that would mean that the total number of cells on the octopus is 25 because we've got 6 on each of the 4 legs plus 1 in the head. That's 25. So that's this world right here. Alternatively, we could do the sort of world where it's black, and we've got 7 or 8 on each line plus the head. That puts us at 33. Now, you recall 33 was the maximum that we could have had. So what that would mean, if that was true, is that all of these cells would have to be on an octopus, plus the 8 perimeter cells. So there would be no sort of spare room for anything in here. And I'm thinking that might be challenging. We'll come back to that in a minute. Let's just wrap our head around this. Actually, that might be really challenging. No, I don't know. We'll circle back to that. I'm just thinking about the fact that we've got to have 7 different digits in column 7. And any of them would have to... So what's the triangular number of 7? 28. Okay, so it could... Because not all of the digits in column 7 are going to be filled on a circle. But it just means that all of these would have to be filled somewhere. But okay, I'm getting ahead of myself. Let's just make sure we understand the foundations of this puzzle here first. So in the world of red, where all the lines go directly to the perimeter, we've got 25 cells on the perimeter. Now that's going to be broken down into sort of different parities. So like that would be one kind of parity. I'll make those orange. And then these would be, we'll make those, I don't know, black for now. Yeah, that's okay. So we've got, in this world, each of the lines would have 4 of one parity and 2 of another. So we would end up with 16 of one kind of cell, one parity, because they would all, basically because the middle is going to be shared by all of them, every line that comes through the center of this, the 2 cells right outside of that head are going to be the other parity, right? So that's true for all the lines. So all the lines would look like this, where it had 4 from one kind of parity and then 2 from another, plus the bonus one in the head. So this would be 9. Now, that means that of the 25 cells, the 9 has to be the odd parity. This is about as far as I think I'm able to take us from how far we got in the stream yesterday. Because you can't get some number of even digits to add up to an odd digit. It doesn't work. So because we do have an odd digit in this world, that has to be the odds. So there would be a total of 9 odds, and that could just be a single 9 that appears 9 times on the octopus, or it could be 1, 3, and 5. But those are the only options, because you need an odd number of odd digits to end up at an odd number. So it's either 9 or 1, 3, 5 in this case. And then 16 is 8, 2, and 6 for the even digits that appear on the octopus. Now, in the world of 32, we've got this kind of a situation here where these become the black cells. Oop, that's not true at all. I messed that up. Oh, no, that is true. This one. Yeah, okay. Those 2. And then these 4 would become the orange cells. So now we've got, in this world, on the black line, we've got an even number on both sides. So it would be 16 and 16, but plus 1 here is 17. So we would be at 16 for one grouping and 17. And again, we would know that the 17 is the odd numbers. And that's because you can't get all evens to add up to an odd number, right? So in either case, we've got 16 worth of even digits on the line, which means that the even digits on the octopus are definitely 8 8s, 2 2s, and 6 6s. That's what, in either world, that's going to be true, because it's 16 either way, and there's only one way to make 16 from only even digits, 8 2 6. So the difference is going to be in the number of odds that appear on the line. Now, so if we're in the red world, black is the odd. And if we're in the black world, the sort of black line world, this world, black is also odd. So in the smaller one, this is an even digit, and that's an odd digit. In this world, this black is an odd digit, and so is that. So actually, we're learning that the center digit is always odd. Either way, it sort of works out. which is quite cool. And we know that, well, do we know that? Hold on. So 1, 3, 5, 7, or 9. So how would we make 17? Okay, so we know that there's no 4s on the octopus. There's 8 8s, 6 6s, 2 2s, and no 4s. And then what is 17? If you add all the odd digits together, you get 25. Is that right? 9 and 1 is 10, 7 and 3 is 10, and 5. Yeah, so 25. So how do we get 17? We need to drop 8, which means either 7 and 1 is missing or 3 and 5 is missing. So in this world, there would always be 9 9s. There would always be 9 9s. Now, okay, so I think that this is a sort of decent aid memoir here in terms of the way that this can be arranged. Now, if we think about just sort of Somedoku, we know that all of these digits are going to be the same, which means they're going to be the same parity. And each of the lines are going to hit that somewhere because of the rotational symmetry of the line. So you can see here, if we tried to make a line not touch that, so it ended there, by symmetry it goes there. So there's no way to not touch any of these. You could, in theory, touch those two cells and have them both be that digit. If you do it those corners exactly. Otherwise, you're going to have a digit from in here and the sort of end of the tentacle in there. But everything hits this. So what we can say is this digit, it must be at least a 5. It must be at least a 5 because we've got 4 lines hitting it. And it can't be a 4 because we know that the even digits are 8, 6, and 2. But I suppose we knew that anyway by this 15 cage logic. Because maybe I've exhausted what I can do with this. Thinking about that. Because actually I can see that these digits have to be 6, 7, 8, or 9. They're 6, 9, or 7, 8. And they're 2 different digits. And they're an even and an odd parity. So let's get rid of my coloring here. What we can say is that this is all going to be some parity. And since we know in row 2, we have 1 even parity and 1 odd parity, then because of this digit has to be the other parity, doesn't it? And that's because this digit is this digit, and so it can't reappear there. So we get that. And this digit is that digit. So in fact, this, because my shading right now is about parity, but the way Somedoku works is that whatever this cell is, it actually must be this. Or in this context, it must be. Because we only get 2 different digits, and it's these 2. And that one isn't that one. So that one is. Right, and that does actually rule out this cell from being on the octopus, because the only way to get there is to travel directly from there, because you can't come in from another perimeter cell by the rules. And these are the same parity. So that's not on the loop. or that's not on the octopus, excuse me, like that, which does mean that every cell comes from, or every tentacle comes from one of these and ends in one of these. And they're always the same parity because they're odd length lines. So we don't know if it's even or odd, but we do know that they have to be the same parity. Now, if they were even, let's say that this was even, because we know a little bit more about that. So let's just imagine that these are evens, the grays. So that's going to be not even. That's odd. Okay, so this is the sort of hypothetical world we're imagining here. Now, whatever this digit is, whether it's 6 or 8, let's just say it's 8. Let's say it's 8. We're going to have a bunch of lines that do this, right? Okay, here's a basic illustration of what it would look like. Very spider-esque, actually. Kind of like that. That's nice. Actually, I think this is broken. I think that this is broken. Oh, that's going to be true for the odds too. Okay. Okay, that's interesting. This is broken, and I'll tell you why. It's because none of these cells can be 8. I should actually extend this. So if that's 8, all of these are 8. And it doesn't matter whether it's 8 or 6 or 2. The maximum number of even or odd digits we can have, different unique even or odd digits that we can have on a line or on the octopus is 3. Because you remember, even if we have, in this world, if it's 9, it's either a single 9 or it's 1, 3, 5. In this one, it's either 1, 7, 9 or it's 3, 5, 9. So there's never 4 different kinds of the same parity. And whichever one of them is going to be allocated to this. And then we've got to have 4 endpoints here. And it can't be whatever this digit is. But we can't have any repeats in the bottom row or the bottom or the far right column. So we would need, let's say it's 8, we would need this to end in a 2 and a 6. But now we don't have another even. So this can't end here because we're out of evens that can be on the octopus. So what we would need actually is for this to do this, to go up. And now we could do, right, like a 2 here and a 6 here. And we're using the 2, 6 that we can get on both of these to fill the extraneous cells. And that's interesting actually because it would use up both 2s if it's even. Now, I think that means 1, 3, 5 is no. 1, 7, 9 in this world is broken. Let me delete that. So if it were the other way around, if we're in this world where the lines wiggle and we have 17 odd digits, odds are on the perimeter here. Okay, so I mean, I proved that this can't be 2, and I think I understand it a little bit better though. Whatever this sort of the edges of the tentacles, you're going to need them. Whichever digit isn't here, both of the other 2 of that parity have to be sort of split on the sort of 4 tentacle tips that hit on this sort of stretch of the puzzle. Okay, so now let's imagine that this isn't that we're in we're in this world, the black world, where these do a wiggle, where these all wiggle. So it would need to be something like this. Yeah, I mean, I won't draw them all in, but you get the idea. Where we're in the 34. Actually, maybe I will just draw them all in, because I'm already almost there. That's kind of a cool pattern, actually. Right, I like that. And just aesthetically, I can actually see that that's broken here, because to make an even digit cage, this would have to be the same parity. But we'll come back to that if it matters. We're in this world now, where all of the lines have a wiggle. We've filled up all of these 25 spaces. And then we've got our sort of 8 things sticking out. And we do have it sort of allocated correctly, where we've got 2 in row 7 and 2 in column 7. So in theory, this could work minus the 10 cage. Now I want to ask, what was the different way that we could have odds? So in this world, it's odd, 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 odd. So we're ending on odds out here. Now, there were 2 different ways that we could have done 17. One of them was 9, 7, 1, and the other was 3, 5, 9. Right? Now I'm going to claim that this one is broken, the 1, 7, 9, and that's because of the need that each of the digits has to be used at least 2. So if you recall, when we were testing with 2, 6, we needed a 2 here to fill one of those 2 cells and a 2 down here to fill one of those 2 cells. But we can't do that with 1. And 1 certainly can't go up here, not just because of the 15, but because we need at least 4. That digit has to be bigger than 1, right? In this side of the perimeter. So 1 would have to be one of these 2 digits. But we need 2 ones, because we need 1 for row 7 and we need 1 for column 7. So this doesn't work. So if we are in the world where this is what's happening, we need it to be 3, 5, and 9. But we could, in principle, I think, make that work. This would be the 9, and then these would be 3s and 5s. Now it wouldn't obviously go there because of the cage, but ignoring that for now. So why does that work? Three, 5, 9. It might. It might. Okay. So either it's this world where the tentacles go straight to the perimeter, in which case they're all ending on the only 2 2s, and then either 2 of the 6s or 2 of the 8s. I wonder how that works in here. That would mean that all of these, well, actually that does mean that either way. All of these are, that's interesting. Okay, so all of these are 2, 4, 6, and 8. If we just think about, instead of, because there's an ambiguity about what the perimeter is, but there's no ambiguity about the center. So all of these are all evens, because one step out from an odd central cell must be even by parity. So this is 8 of 8 of the even cells in the grid, and that's a genuine pencil mark. Okay, let's try to get back to what we know at this point, which is some things, but I don't feel like I've really progressed very far. Okay, so we know, yeah, I'm going to keep that, but just note that that's not like a real pencil mark, right? These are real pencil marks. This is a 1, 3, 5, 7, or 9. It can't be 7. Because it's either 3, 5, 9, or if it's here. And then if it's this, it's 1, 3, 5, or 9. So that's never a 7. There's no 7. There is no 7 anywhere on the octopus. Does that mean there's no 7 in the grid? If we're only taking 25 cells, is there enough room for spare 7s? It feels hard. We would be taking... so there would be we're taking 8 cells of this middle ring here, no matter what. That's 2, 3, 4, 5, 6, 7, 8. That leaves 8 remaining if we're in this world where we don't wiggle. There would be 8 remaining cells in this ring. So okay, there might be 7 missing 7s in the puzzle. That feels hard just because we could only get 1, 2 in all of those, and none in these. So then there would have to be 5 of the 8 cells would be 7. I mean, that seems kind of unlikely, but not necessarily impossible. Oh, if I could prove, that would give me a 6, 9, which would be actually very interesting. Here. So maybe that does matter. Maybe I need to think about that a little harder. Could I possibly get... Well, okay, actually... All right, so if this was 7 and this was 8, then for sure 7's not the perimeter. Oh, 7, yeah, okay. So these cells are on the edge. So this is definitely never 7. So if this is a 7, 8, these are all 8s, definitely. And that tells us that we're going 8 odd 8. It would be directly. It's that version, right? It's this. Yeah, okay. But then, no, that doesn't work. That's broken. This is not 7, 8. I'm gonna claim. Oh, this is really, really nice. Okay, I'm not positive about this, so maybe I won't claim. I won't claim, but I think this is broken. And that's because all of these digits are 7 and 8. But if you recall the way the lines had to work, the line we have to have 2 of these because we need 2 of these down here. Because we only have 3. Oh, this is so good. This is so good, pedaling pianist. Because we only have 3 different digits from each parity. We have to have 2 of the lines hit row 7 and 2 of the lines hit column 7. But the rotational symmetry of that means we have to have 2 of the lines hit row 1 and 2 of the lines hit column 1. Now, if this was a 7, because we've proved that 7 can't be anywhere on the octopus because it doesn't work. Oh my goodness, I'm blown away by this actually, because it's 359 or it's 135 or it's 9. So we can't get there. We can't get to any of these 8s because the next step needs to be an odd digit, and the only odd digit available is 7, and that doesn't work. So this isn't 7 8. This is a 6 9 pair. That's cool. But unfortunately, I don't think that tells me about which is which, does it? I don't think it does. But it does mean that 9's on the loop. I mean, 9 was always, no, it could have been 135. Now it's definitely not 135 because 9's the only odd digit in this row. And we're definitely hitting an odd digit in row 2 before we get to the 2 endpoints in row 1. You know what else I can do? I just realized I can X that off because we can't go there. We need them to be in this stretch because we need these 2 digits repeat there, and we need all 4 of those. So it definitely doesn't go into the corner cells. It's 2 in here, 2 in here, 2 in here, and 2 in here. Right. Okay. Ooh, I suddenly feel like maybe there's a real chance here. Okay. So now we know that 1 isn't. There's no 1 because it's either 359 or it's just 9 9s. Can it be just 9 9s? That would mean that we would need 2 9s in here. These would be 6s. All right, so this would be 6. I'm trying to imagine this scenario. So that's 6. This is a 9. This is a 6. Now we're going to have 2 9s that it's going through. Something like that. No, it doesn't work. Oh, yeah, no, that doesn't work. This is really cool. The reason that doesn't work, remember, is if it's this scenario where even is on the perimeter, then we're in this world where there's no zigzagging. And when there's no zigzagging, that means that all of the odd digits exist in this ring. Because we go odd here, even in that ring, odd in this ring, and then even here. Because we don't have a zag in our lines. And that means because we know that 9 has to be on from this sort of row, then, and we know because we have to hit 2 in each of these little strings, that we need 2 9s here somewhere. Somewhere in this stretch, we need 2 9s. But now we can't get enough different digits in column 6 because that's a repeat and that's a repeat. So we only have 2 digits there. We could get 3, 4, and 5. It's not enough. We need 6. And it would have to be 9s. That's so good. So now we know that that's not the case. This isn't the world we're in. We're in this other world, which is crazy because that means that all of these cells have to be filled. The entire sort of central region, all is going to be filled. And I think that this 10 cage is going to come into its own now. Okay, so all of these are going to be on the octopus, plus 2 over here, 2 over here, 2 over here, and 2 over here, but with better symmetry. Something like that. Yeah, okay. That's going to be roughly the shape of our octopus. And we know that it's 3, 5, and 9. The digits that appear on our octopus are exactly 2, 6, 8, 3, 5, 9. And if we add all that up, we should get to exactly 33. So let's do the math here. 2 and 8 is 10. So I don't know why. Why did I start? Yeah, that makes sense. Okay, 2 and 8 is 10. I'm going to delete them as I do it. 10, 19, 25, 33. Yes. Yes. Okay, so that all works. So the digits are 2, 6, 8, 3, 5, 9. That's what's going to be. And that's just an aid memoir. So I'm going to note that here because I know that that cell's not on our octopus. So I'm just going to leave that there to remember that those are the digits that are appearing. Whew, I feel great about that. And we know that this is all 9s. So we have genuine digits in the puzzle. That's a 6. That's a 9. Right. Wow. Okay. So we also know that 6 could be on. No, it ends in odds. So there's a 3 and a 5 somewhere in here that are gonna where it ends, and then there's a 3 and a 5 somewhere down there where it ends. Okay. So what I want to think about now is these 2 digits, because they're the same parity. What we can't do is this as a wiggle, because this is even, so this needs to be odd by the line, but then by the line this needs to be even, but an odd and an even won't give us to 10. That'll never work. So these 2 digits can't be on the same line. So that definitely makes me think about that cell, right? I'm inclined to think that it has to be that line, right? It's certainly not going to be this line that goes and does that. That doesn't work. Could it be there? Could it be there? Well, I think it couldn't do that, but maybe that. for the reason being that we have to get 2 of them over here. I mean, I'm not even positive that that's true. So why is this broken? Then this would certainly have to do that. This would have to do that, sort of like this. We would kind of end up in a pattern like that. I mean, we don't know exactly how that ends, but yeah, like that. I think, if that's what that does. And now what does that do? Well, I can see that this doesn't work. In fact, maybe that's a better place to start. Let me undo all of this, because I actually know the parity of this cell. That's odd, which means that, and this is definitely on, this is I think where to start. Because all of these cells have to be, to get to 33, we need all 25 of those, plus 8 cells in the perimeter. So this is definitely on one of the tentacles, but it can't be out somewhere and then into there. That doesn't work, right? Because because of the parity. So it would be even, odd, odd, which doesn't work. So this has to be the next step on a line, which I think means that's forced, which means that's forced. And now, no, I was going to say it has to go, I was thinking it has to do that, but that's wrong because we need to even somewhere. So we could either do that or we could do that. But this is forced. And I think maybe that restricts our ability to do this kind of shenanigans. Because if that's true, then we run out of space down here. Okay. So this one can't take that. This one can't take that. So this and this are on the same. What I don't know is whether it does that or that. Although, well, no, I really don't know that, do I? Okay. All right. So the other question that's maybe worth thinking about is actually what I want to do. Sorry, my brain goes in multiple places at a time. I'm going to highlight this and then do that to note that that cell's on that line. In fact, I think I'm going to undo all of these. It might not matter, but it makes me feel good to have different colored lines. So we'll do that. There we go. That feels better. Now we're making progress. Right. So we have a total of 33 cells in the octopus. That's going to account from those digits. But we have remaining. Oh, no. Okay. Because we're going to have extra 9s here, aren't we? Yeah, we sure are. Okay. I was wondering if we could do math to figure out what the other digits could be, but that's not quite right because we have the ability to have, once we have 9 9s on the octopus, we can put as many 9s as we want elsewhere. That doesn't matter. It's only a digit that doesn't appear on the octopus that we get the sort of anti-octopus constraint on the back end. But what I'm wondering here is we know that, for example, we're actually going to have quite a lot of 9s in the puzzle because we've already got 7 and 6 is 13. But only of those 13, only 4 are being hit by lines. So we've got a bonus 8 or a bonus 9 9s. So we've got 33 cells plus at least 9 extra 9s, which puts us at 42 total cells accounted for. I suppose perhaps this sort of back end is going to be interesting, isn't it? How do we get, well, let's see, how many different digits do we have in the thing? 2, 3, 5, 6, 8, 9. That's only 6 different digits. So we do know for sure that there's at least one digit that must appear in this column and that must appear in this column that doesn't appear, that's not one of these digits. So there's either a 1, a 4, or a 7 somewhere in the puzzle. Now 7 does feel awfully tough. 7 feels awfully tough. Well, I'll tell you what I'm going to do. I'm going to make all of these from 6 or 9. Now, could there be some hidden 7s over here? No, because all of these are, yeah. Oh, right. Oh, I'm sorry. I'm being daft. All of these are on the octopus. So the remaining cell that must exist is only from here. Oh, this is brilliant too. The remaining cell that's not on the octopus only exists here. And that means it's a maximum of 2, but 2 is on the octopus. So the other digit that must exist in the puzzle that isn't on the octopus, there can only be 1 now, and it must be a 1, and it actually goes where I've got my aide memoir set up here. That's a 1. That's beautiful. Okay, so let me just run through that logic again, just to be clear. We need 7 different digits here. We only have 6 unique digits that appear on the octopus. I'm going to redo my aide memoir over here now. They are 268 for evens and 359s for odds. So that's only 6 different digits, but we need 7. So, but all of these are digits that appear on the octopus. All of that. All of those cells. So we only had these different sort of places to choose from. So if it wasn't a 1, we could have a maximum of 1 of them over here and 1 of them over here. But 2's on the thing. So it has to be 1 and it has to go there. That's so cool. Yeah, I love that. Now we know, actually, that every other digit in the puzzle, every digit in the puzzle we could do. I mean, it's ridiculous, but we could do. Well, okay. Oh my goodness. Pedaling pianist. It's just so good. How do you make 10? How do you make 10? 9-1 doesn't work. 5-5. Oh, 5-5 could work. Oh man, it's gonna be 5-5, isn't it? I was gonna say that it has to be 2-8. 3-7 doesn't work. 6-4 doesn't work. That's amazing how that worked out, actually. So this is either 2-8 or 5-5. Could this be 5-5? No. Could it? No. Oh my goodness. This is a really intricate step too. Okay. So, wow. I don't think that this can be 5-5. If this is 5-5, watch what happens here. What I wanted to ask, what's this? And at first, I don't know, I was thinking palindrome, so it has to be 9, but that's not true. This could, if this is, actually, I think it does have to be 9. Oh, it would have worked either way. I think that even if, because this is, let's say this is a 9, so we still have a digit to spare over here. We know that this digit has to be odd. But we know that this line is going to take an odd, this red is going to take an odd in one of these and then an even in one of these. So the composition of the digits in column 2 has to be even odd. It can't be yeah. Oh, okay. So it can't be like 5. There can't be a different odd digit to place here. Sorry, I'm losing my train of thought. Yes. Okay. So the point is, let's see if we can get back to the point. I don't know what this cell is, but I do know that in this column, we need an even and an odd, because this red line is going to wiggle. It's going to take an odd cell, an even cell, and then go to a 9. So we can't have this cell because it needs to go into an odd. It has to be the odd in this column, and the odd in this column is a 9. So I do know that that's a 9. So now if this is 2 5s, we're broken. It's too many. I was going to do this actually a much more intricate way, which was to say, can the other odd in this column be 3? No, because we need one of the 3's here and one of the 3's here. So the other odd in this column, if there is another odd, in order to not make this a 9. Okay, sorry. The way I was thinking about it was, can this be not a 9? It's an odd. Can it be not a 9? Because if it's a 9, we can't have 2 5s because that's too many pairs. So I was thinking, well, what's the other odd it can be? Well, it can't be 3. And if it's 5, it's the same thing, because that would be creating 3 5s and it would break. But it's actually simpler than that. This just has to be 9 because there has to be an odd and an even in column 2. We know what the odd is. It's a 9. We don't know that it's 6. This could also be 9, and we could have like 8s down here. That would work fine. So we don't know that that's a 6. But we do know that every odd that appears in this column is 9. And that actually tells us that this is even. That's 2, 6, or 8. I think I can get rid of this now. Right, so this can't be 5s because that would be too many repeated digits. So that is a 2, 8. Now this can't go straight into there. So we actually do know that the pink line has to zag before it gets into there. So that's quite nice. Now, how do we get this cell filled? Well, it's got to be green, doesn't it? That's the only way. So I think we're actually going to get this now. So green goes like this. Black now. Well, let me do the sort of converse of that. We can do this goes like that, I think. Now this cell has to be taken, so it's got to be taken by black. So that becomes black. And now red takes these cells, but we don't actually know at this point the order yet. So what do we know? This is even. That has to be odd, so that's a 9. This has to be even, so that's a 6. This is a 6. Now this has to be even, so that is a 6. So we do know that the even digits in this column are 6. So now it's a 6, 9 all the way. That becomes a 6 here. This is 6 and 9. Oh, I can leave those in actually. That's a 6, 9. Both of those appear on it. This can't be any more 9s. So we can't have any more 9s here. So this digit is 3 or 5. Right. What do we know then? I mean, this is amazing. How do we finish it? We know what these digits are, don't we? Because we have to have 2, 6, and 8, 3, and 5. So this digit, this feels so lazy, but this digit's smaller than that. So this is an 8. And this isn't 2. There we go. Feeling very helpful using the inequality. So how many 6s have we used? 1, 2, 3, 4. 4 of the 6s are gone. 1, 2, and 1, 8 are gone. 4 of the 6s. Okay. This is 9. If we used all of the evens, that would have to be even also. So, well, okay. Remember that wherever the 3 goes down here, it needs to be on a line. And wherever the 3 goes here, it has to be on a line. So that's 2 of our 3 3s allocated. So if that's a 3, then that's the third 3. Now, do we need to have... We do, don't we? We can't have 2 5s here. The odd digit that must appear in one of these red cells, let's make it a 5. That's fine. But that can't be a 5. Oh, so okay. this is where our last 3 gets taken, because we need 3 odd, there's going to be 4 odd digits, and we can only have the repeated 9. So one of these is going to be a 3 or a 5, and then that's going to be a 3 or a 5. And they have to be different. So no other 3s. 1 3 here, 1 3 here, and 1 3 here, and that's all the 3s. So that's not a 3. And this isn't a 3, so that's a 5 or a 9. This is 2, 4, 6, or 8. We have 9 and 6 plus 1 other digit. And that other digit surely has to be an even digit, because these can't all be 6. We already have a bunch of 6s on a line. We have 1, 2, 3, and 4 6s. So we could make 2 more 6s there. But then what are these 2? If this was a 3, for example, that breaks, because now 3, 6, 9 are our only digits. We can't make all of these 6s. So that's not a 3. It's not the world's great, or 5, sorry. That isn't even. Not the world's greatest deduction, but there you have it. Now, actually that's very useful, because this line has to end in an odd digit. And so where does it go? It can't go there, it can't go there, it has to go there. So we've actually completed one of our lines here. It's got to do that. And now this digit isn't an 8. It's 3 or 5, which means that digit can't be 5. It's 2 or 3. Wow. Right. So can we do something similar in row 3? No, because we don't have a 6 here. So these could all be 8, and that's fine. These could all, we could literally make all of these 8 in principle. We would break Somedoku because we wouldn't have 3 different digits, but that just means there's plenty of flexibility there. Right. So what's the next step then? If this is 3, that's a 2. That's an 8, which means we're at 6s and 8s lands. Well, okay, one of the 2s is here. We only get 2 of them on the line. So one of them's there. Okay, this can't be an odd digit, can it? Oh, it's so good. Yeah, right. So remember, we've got this odd digit, one of these odd digits. We don't know which one, but one of them is. And then that, the double 9. So that's that's all 3 different odd digits plus our repeat in the column. So these 3, the other one of these, the even in red, this cell and this cell must be 3 different even digits, which means that isn't 3 or 5, which gives me a 2-8 pair in the row, which makes that a 3. That's a 5. Now this green goes there. Pink could, in theory, reach it, but then green would be locked out. So green goes like that, because all the 3 and the 5 have to be taken. Now this pink goes into one of these 2. Do we know which one? Well, oh, right. Okay. I'm missing obvious Somedoku logic here. That has to be a 5 because we've already had our pair of 9s there. So that becomes 5. Now, we can't have a repeat, so that's not 2 or 8 down here. Oops. Forgive me. So that's 4 or 6. In fact, it's not. Why do I have 4 everywhere? isn't it just 2, 6, and 8? That's just a 6. I feel that's very silly. I'm sorry. No, I just mark these because that's from very early on when I realized that this had to be evens before I realized that there were 2 8s and 6s. So there's no 4s anywhere in the grid. It's all 2, 6, 8, 3, 5, 9, and then our fantastic 1 hanging out down here in the corner. Right, so that's a 6. That's a 2, 8, 5, and 9. So, that means, I guess I didn't quite realize this, but yeah, all of the digits have to appear because there's only 7 different digits in the puzzle, but 1 doesn't go anywhere else but there. So in fact, all of the 6 digits on the octopus have to appear here with a 1 repeat, same as it was sort of here, which I didn't internalize that. I just sort of pieced it together. But we need a 3 there, so that's the 3, which means that pink has to go there. Because if pink picked up like a 5 there, that 3 needs to get taken, which it could no longer do. So that's closed off. Very cool. Now, I'm very curious how the 2 6s and 8s. I mean, it must just be the sort of maths on it there. Okay, but that means that this is a 6. There's a 6 in there. And it's from 6, 3, 5. And that does mean that there's a 6. That's another 6 on the line. So there's a 6 on the line there, a second 6 on the line there, a third, a fourth, and a 5th 6 on the line, and a 6th 6 on the line. 1, 2, 3, 4, 5, 6. That's wild because we have a 2, 8 here. We need to have a 6, and we know that both of these cells are on the red line. That's crazy. So now we know that none of these are 6s. That's all 2s and 8s. Can we do that with 5s too? We got 1, 2, 5. I was wondering if I could make that a 9. We do have a 5 here. That's 3. We have a 4th 5 over there. That's 4. Do we have our 9s already locked up then, maybe? 1, 2, 3, 4, 5, 6, 7, 8, wherever that one lands, 9. We do, don't we? Yeah, that makes sense. Okay, so that has to be a 5. Because we're going to get 1, 2, 3, one of those, 4, and then one of these is 5. There's nowhere else to get it. So in fact, that has to be a 5. And that all sort of works out. Okay. Wow. So I think all of these have to be the same digit because we've got a 9 plus a 2 or an 8 plus a 3, 5, or 6. These don't, there's no overlap there. So those are 2 different digits, and that's a 3rd different digit. So these can't all be 2s. Those have to all be 8s. And now either this is the same digit as that, which could happen if the line went like this, right? It might not be possible for other reasons. I don't know, but I'm not quite ready to rule that out yet. Okay, so we do know that one of our 2s is located there, so most of these are 8s. Well, what are these? Let's just do that. Let's start there. We have 2, 8, and 5 to place there. This can't be 2. So 8, 9, and 3, 5, or 6. So that's 8 or 5. It's not 2. Okay. Does this need to be 2 different digits? If these are all 8s, even if we go 1, 2, 3, we We need 5 different digits. 3, 5. That could be possible, actually, if this is all 8s. I'm not prepared to rule that out. So what's going on here? If that's the 6, then that's the 8, and it has to go ding, ding, ding. Yeah, if that's the 6, then this can't be a 5. So the line can't go from even to even, so it would have to go even, odd, even. But then that's even, so now it has to go back down to there to pick up a 5. If this is the 6, then it has to go up here, 3 or 5. Well, okay, so this can't be, oh no, 5, 8. Yeah, I don't know. Oh, how do we wrap this up? I would hate to get stuck now. I'm sure it's just because I'm doing this puzzle very late. Hoping to surprise the pedaling pianist tomorrow with this solo solve of this beautiful puzzle. But I'm up past my bedtime now. So how do we put a bow on this beautiful thing? 9, 6, and 8 are the 3 digits there. So those can't be 2s. Those are 8s. That can't be a 2. That's an 8. Do the easy Somedoku logic. So that's 2. That's 8 now. That's 2. Now we've got 5, 8, 9 is only 3 different digits. So that has to be the other 2. That's now all of the 2s on the lines. We've got them both there and there. So these are both 8s. Okay, that's a flurry of activity. Now what? We have in row 4, 9, 8, 5. What does that mean? It means if this was a 2, then neither of these could be 6. They would both have to be odd. So it would be 9 and 5. Oh, I think that's true. Oh, that's kind of weird, isn't it? I forgot because we have rotational symmetry. If it goes there first, then it goes there first. So these have to be the same parity, no matter what. Actually, I'm going to get rid of that coloring here. And that one, I didn't end up using it at all. And now I want to note that these are the sort of same parity. And these are the same parity. So if orange is even, those are both 6. I think it's more interesting if they're odd. If it's odd, that's 9. I still don't know what that means. All right, so if these are even, that's 6. And now we're at 9, 6, 8, 5. 6, that would have to be 6 also. So 9, 6, 8, 5. That could still be 8 or 5. But that couldn't be 2 in that world. If this is odd, then that's 9. It could be 5, and then that could be 2. What am I missing? 2, 5, 8, 3, 5, 6, 6, 9. Did I count all? Yeah, I did, right? Because this is a 3, that's a 3, that's a 3. So that's all of my 3s. We've got all that. It's just we just have to figure this out. Okay, use your brain. Figure out the puzzle. I'm close to bifurcating. Just so not that I have no doubt that that's not necessary, but it might be necessary given my sort of cognitive abilities at the moment. Maybe we'll count this row. 9, 8, and 2. That's only 3 different digits. So if that was a 9 also, that's still only 3 different digits. We need 5, so this would have to be 2 different digits. So that would have to be 5 and 3 if that's 9, right? If that's 9, we're at just 3 different digits. We need to get to 5. So the only new digit here would be a 5, which would make that a 3. And if that's a 5 and that's a 3, then we need to get to that 5, which means that has to be an even digit, 6 and 6, which works with that being 9. 6 and 6 and 9, 5 and 3. This line goes like that. Like that. I think that all works, actually. So what's the... that was it going into orange. So why does this break? If that's... All right, I'm just doing it. I'm sorry. I can't see it in my head. I don't have it. 6. So it would have to go like that, like that. Now we've got 9, 8. This is now an even digit, isn't it? Odd, even. So that becomes a 6. 9, 8, 6. So that has to be 8. That has to be 5. Now we've got 9, 8, 5. This has to be 3. 5 there. 2. Ah! Oh no. Okay, I got it right. But I felt like... So how does it break the other way? Sorry, I was just like following the path there. So why does this break then? Because that actually felt good to me. Here what happens is we get 9, 6. This 9 now means that we need 2 different digits. So that becomes 5 and 3. This becomes 5 and 6. Now the line goes there, 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 like that. Now 9, 8, 5 all works. That becomes 8, and that becomes 2. And we get 2, 6, 5, 8, and 9. Too many digits in row 4. Oh yeah, that was a little tough for me to visualize at that point. So okay, now that I know how it breaks, let me go back and see if I was thinking about it right, I could see it. If this is a 2, maybe that's the way to think about it. If this is a 2, we've got 2, 5, 8, and 9. That's all 4 of our different digits. So that has to be a 9, which means that has to be a 5. Right? Yeah, so 9 and 5. But that actually works. And then we have 6 and 6. So 2, 6. Oh, I could see. Okay. I can see that. It's a little hard. But these become the odd versions. If this is a 2, these become the odd versions because we need we can't have 6s because we would be at all of our digits. So these become odds. These become 6s, which means that we end up there. But remember, I said if this I did realize this at a certain point. It was hard to see, but I said if it ends there, it has to jump back down because that's a 6. This would be a 6 in this case, which means this can't be a 5. So it needs to go pick up a 5 there. But we had hypothesized that this was a 2 to start. So in fact, this isn't a 2, which does make this a 2. And now, 2, 8, and 9 is only 3 different digits. We need to get to 5, so that has to be 6. that has to be 6. So now the line has to do that into black first. So that becomes 9. That becomes, I'm not sure. Well, okay, this goes into 5, which has to go here, right? That becomes 5, 8. Now we have 9, 8, and 5. So that has to be 3 and 5. Okay, so we got there. We got there logically. Yeah, wow, very cool. Oh, I love that a lot. All right, so there is a link to this puzzle if you made it all the way to the end. I forgot to say that at the beginning. This one and our collaborative puzzle, which is this thing. There's a lot of similarities, but there's definitely some distinct logic that's going to be present in this puzzle as well. So I hope you give it a shot. Really, really pleased with the way that this one came out. But that's going to do it for tonight. Thanks for watching. Have a wonderful rest of your day. Cheers.